Alright, so let's pick up where we left off. This is determining extent of reactions. Okay, so another application here, determining the solubility of an insoluble salt if you're given the KSP. Okay, so if you're given the KSP of MX2, again, this is a fictitious compound, so you can just say that that breaks up into M and 2X, okay, with some charges there. Okay, so what would be our KSP for this, the expression for KSP? KSP would be the concentration of M times the concentration of X squared, right? So let's set this up. You have initial conditions would be, you have an excess amount of solid because you're making a saturated solution. So anytime you're dealing with a solubility problem, you have, in order for you to get an ion product, a Q that's equal to KSP, you have to have some excess, at least some excess solid there. The activity would be 1. Okay. The changes would be what? You have minus X. So X would be the solubility in moles per liter. And you're going to make X moles per liter of M and 2X moles per liter of X. So at equilibrium, you still have an excess here, okay? At least you have to have at least some solid. You have to have a saturated solution, and then you have X moles per liter of M and 2X moles per liter of X. Okay, so what's our expression for KSP in terms of X? This is going to be X times 2X squared. And we're given the KSP is 1 times 10 to the negative 10, so we say that that's equal to 1.0 times 10 to the negative 10. What would be our X? Therefore, here, you'd say X times 2X squared is how much? What is that? 4X cubed, right? So that's equal to 1.0 times 10 to the negative 10. So how do you solve for X? X cubed is 1.0 times 10 to the negative 10 over 4. So X would be equal to the cube root of that number. So what is that number? 1 times 10 to the negative 10 divided by 4 equals that. And take the cube root of that, so that's 2.9. Oops. Okay, this is 2.5 times 10 to the negative 11, and the cube root of that, oops, is 2.9 times 10 to the negative 4. So the solubility is 2.9 times 10 to the negative 4 moles per liter. So if you know the KSP, you can predict how far your solid will dissolve. Now, one thing you need to worry about here, if you're given a real compound, okay, if your anion, let's say your anion is carbonate, okay, the solubility that you calculate would actually be less than what you would expect, what you would get experimentally. And the reason for that is why? Your carbonate can actually hydrolyze, right? And it will give you HCO3 minus plus OH minus. So there's actually a reaction that's taking carbonate away, so it's going to shift your equilibrium further to the right. So the actual solubility in reality is going to be a little higher. If your ions can hydrolyze, you have reactions that are removing those ions. So if you're removing these ions right here, okay, if you have some other stuff in your water that are removing this, then the Chatelier's principle says that shifts that equilibrium further to the right. Okay. Now, for simplicity, unless you are told to consider the hydrolysis and you're given the actual values for the equilibrium constants for the hydrolysis, just assume the simplest case, which is ignore the hydrolysis. Okay. And the calculation gets a little bit more involved when you have to take into account the hydrolysis. Here's another example. This one is precipitation. What's precipitation? Two ions getting together to form a solid. So it's just the opposite of the dissolution process, right? So if you're talking about precipitation of calcium carbonate, that would be from calcium chloride and sodium carbonate. That would be calcium from the calcium carbonate and carbonate from the sodium carbonate. That would be your net ionic equation, right? Calcium from the calcium chloride, carbonate from the sodium carbonate gives you calcium carbonate. This is just the opposite of the dissolution, which is calcium carbonate gives you calcium ions plus carbonate ions, right? The KEQ for this is 1 over the KSP, right? The KEQ for this is the KSP of sodium carbonate. We can analyze this problem. We can solve this problem using either of these two reactions. This is basically the same reaction, and you just make opposite assumptions as far as where the reaction goes. Because if your KSP is since your KSP is very small, it would mean the KEQ for the precipitation would be very large. Okay, so let's work this problem out using traditional way it's done in textbooks. So let's just do it this way. Let's use this one right here. You're given equal volumes of 10 to the negative fifth molar calcium chloride and 10 to the negative fifth molar of sodium carbonate. So what would be our initial concentration for calcium carbonate? Well, this is excess, right? Solid. Actually, there's none, right? There's no calcium carbonate because you're mixing two solutions. What's the initial concentration of calcium? Is it 10 to the negative fifth? You're mixing equal volumes. So your volume has doubled. So it's no longer 1 times 10 to the negative fifth. What is it now? It got diluted twofold, right? So your initial concentration of calcium is only 0.50 times 10 to the negative fifth. Okay. So initial concentrations, 0 for you don't have any calcium carbonate. This is 0.50 times 10 to the negative fifth. Your carbonate is also half of this original amount concentration because, like I said, you've doubled the volume when you mix them. So this is 0.50 times 10 to the negative fifth. This question is asking whether precipitation will occur. What does it mean if precipitation occurs? That means which way does the reaction go? The question is really asking, will the reaction go to the left, right? Going to the left is precipitation. And when will precipitation occur? You remember? When will the reverse reaction occur? When you comparing Q and KEQ, when Q is greater than KEQ, right? It goes to the left. Remember from your earlier lesson. So all we have to do is calculate Q in this case. What's our Q? Q is calcium ions times carbonate ions. What's our calcium ions concentration? 0.50 times 10 to the negative fifth. And your carbonate is 0.50 times 10 to the negative fifth. And that gives us 0.5 times 10 to the negative fifth. Okay, square it, right? It's 2.5 times 10 to the negative 11. Compare that to KSP, which is our KEQ. What's KSP here? 5.0 times 10 to the negative 9. So, A, yes, T, no. Will precipitation occur given that Q is 2.5 times 10 to the negative 11 and KSP is 5 times 10 to the negative 9. I lost my clicker again. So is it going to precipitate or not? Yes or no? Answer? No. Okay, why not? Q is less than KSP. So, will the reaction go forward? No, there is no solid calcium carbonate, right? It can't go forward as written because you don't have any calcium carbonate, but it will not go in reverse either. Okay?
So KSP versus Q. Q is telling you what? That's
Q versus Q versus KEQ. KEQ in this case is KSP. If Q is less than KEQ, the reaction will go forward until Q becomes equal to KEQ. In this case, Q is less than KEQ. It will try to go forward if it could, but it couldn't because there is no calcium carbonate solid. But it's not going to go in reverse. Okay? If this does go in reverse, then you have a precipitation reaction. Okay, so if you exceed the concentration, the value of the KSP, if your concentration is such that your Q exceeds KSP, then you'll have precipitation. Okay. By the way, Q in this case, when we're dealing with KSP, Q is also known as the ion product. Okay. So you might encounter that term. So when you're dealing with KSP and solubility equilibria, ion product refers to the reaction quotient that you can compare with KSP. Okay. Let's look at this question right here. What's the solubility of calcium carbonate in a solution that is 1 molar in sodium carbonate? KSP is 5.0 times 10 to the negative 9. So what's our reaction here? Dissolving calcium carbonate solid, KSP. So what's the product here? Calcium ions in aqueous solution plus carbonate ions in aqueous solution. Initial concentration. Since we're talking about solubility, we're going to assume that we have enough solid to dissolve. Okay, so we're just going to have excess amounts of calcium carbonate. None of this and none of that. What would be our changes? The solubility is x moles per liter, so minus x moles per liter of solution. So you're going to get plus x and plus x. Okay, at equilibrium, what will we have? You still want, if you want to be able to calculate the solubility, you want to make sure you still have an excess of the solid, right? And so you have x moles per liter of calcium and x moles per liter of carbonate. Oops, I forgot something. This is 1 molar in sodium carbonate. So what's my initial carbonate concentration? It's not going to be 0. What is it? 1.0, right? Your sodium carbonate is going to fully ionize into sodium ions and carbonate ions. So my initial concentration is 1 for carbonate. So I have some other source of carbonate. So Le Chatelier's principle tells you what? How is this equilibrium affected by putting an extraneous source of carbonate? Shifts which way? To the left. Okay, so you would expect this to be not quite as soluble. Your X would be not quite as much as what you would expect if there wasn't any other source of carbonate. Okay, so our final equilibrium concentration here is 1.0 plus X for carbonate, right? So this is going to be 1.0 plus X. So let's solve for X. What do we get? X times 1.0 plus X, that's your calcium ions, and this is your carbonate ion. Concentration is equal to KSP, which is 5.0 times 10 to the negative 9. This is your KSP. Okay? And to avoid confusion, let me get rid of that X there. So 5.0 times 10 to the negative 9. That way I don't have to worry about that x and that times symbol being confused. Okay? How do I solve for x here? Do you think, okay, right here you have a quadratic equation, right? So this is where you try to look for a time saver. Do you think I can neglect this x compared to 1? Look at this KEQ. Very small number, right? So this reaction will hardly go forward. I don't expect that x to make a difference to the total carbonate concentration. So I'm going to make that assumption that x is very small compared to 1. So how would I simplify this equation? X times 1.0 equals 5.0 times 10 to the negative 9, right? How do I solve for x then? This makes it very easy. X equals 5.0 times 10 to the negative 9. Is that very small compared to 0.1? Compared to 1? What is 1 plus 0.000000000? That's 8. And then 9. 5. That's still 1, right? So I can ignore that x right there. What do you notice about your solubility? It's a very small number, right? Now, you might get a bigger one if there wasn't that 1 right there. What would you get if the 1 wasn't there? Did we calculate the solubility earlier? We did not. Okay, so let's calculate it without the carbonate. Without the sodium carbonate. What would it have been if you didn't have sodium carbonate? You would have said x squared equals 5.0 times 10 to the negative 9, right? And then you would have said x would be the square root of that. 5 times 10 to the negative 9 square root. Where's the square root? Second root is 7 times 10 to the negative 5. Okay, this is much smaller. This is without sodium carbonate. And this one over here is with the sodium carbonate. The solubility decreases. This is known as the common ion effect, which is really nothing more than just Le Chatelier's principle in action. Okay? By putting this common ion, you're lowering the solubility of your calcium carbonate because the reaction is shifted to the left. So you're suppressing the dissolution of calcium carbonate. So this is known as this is an example of what we call the common ion effect. Now, like I said, we're assuming here that we're not taking into account here the possibility of carbonate hydrolyzing. Okay, so this is reality is not quite as simple as this, but we're just going to make things simple. We're just going to do it this way. Okay. All right, let's take a look at this question right here. What's the pH of a solution obtained by mixing 50 ml of 0.1 molar sodium hydroxide with 25 ml of HCl? Sodium hydroxide, strong base, HCl, strong acid. What's your net ionic equation? H plus hydroxide gives you H2O. What's the KEQ for this? 1.0 times 10, 0 times 10 to the 14, a very large number, right? So what's our initial concentration? Okay, let's just do moles first, and we'll figure out concentration later, because we know this is going to go all the way, right? So let's just do moles. 50 ml times 0.1 is how much? 50 mils times 0.1 millimoles per mil. That's 5 millimoles, right? So that's 5 millimoles of HCl, sodium hydroxide. So your hydroxide would be 5.00 millimoles over the total volume, which is 50 mils, which is 75 mils. The total volume is 75, so over 75 mils. That's your initial concentration. Okay. Molarity times volume gives you moles, but if you use milliliters, that will give you millimoles. What's the initial concentration of HCl, of H+? 25.0 milliliters times 0.100 moles per liter. That gives you 2.5. Okay, liter cancels out, so that gives you the answer in millimoles. So initially your H plus is going to be 2.5 millimoles divided by the total volume, which is 50 and 25 is 75 mils, right? So those are your initial concentrations. And we don't worry about water, we got tons of it, right? No, not tons, plenty of it, excess. What would be your changes? 2.5 versus 5, 1-to-1 ratio. Which one is the limiting reactant? This is your limiting reactant. Right. And this KEQ is very large, so you know it's going to go all the way, right? So you're going to have trace amounts left here, right? So you have, okay, you're going to pretty much lose everything here, minus everything, right? Right? And how much do you have here? You're going to lose 2.5 millimoles over 75 mils, right? In other words, the amount you lose would be minus 2.5 millimoles over 75 mils for HCl, for H+. So at equilibrium, you would have virtually nothing here. It's a trace amount, okay? And we're just going to call that X, so we can figure out what that is. So what's 5 minus 2.5? So this is going to be 2.5 millimoles over 75 mils. Okay? And water will just be excess, so you don't worry about the water. Okay? So, in other words, what we're really saying is, assume it goes all the way and then back it up a little bit, okay, so that you have a trace amount of H plus in your reaction mixture. Okay, in other words, this is really going to be there's going to be a plus X here. Okay, if there's X amount left here, then there's going to be a little plus X here. But this extra X will be negligible compared to this, because that's just a trace amount. So H plus. Okay. So we're going to say then what? 1 over X times 2.5 over 75, right, is equal to KEQ, which is, because water is in your activity of water is 1. Products over reactants. H plus and hydroxide are reactants here. So you can say that's 1 over KW. Or you can also say, so this is H plus, and that's your hydroxide, is equal to 1 over KW. Okay, or you can say, if you take the reciprocal, you can just say X times 2.5 over 75.0 is equal to KW. So I can solve for X. What's my X going to be? KW times 2.50 over 75, which would be how much? 1.00 times 10 to the negative 14 times 2.50 over 75. How much is that?
Why did you say at the beginning K was 1.00 times 10 to the 14, and now it's negative 14?
Oh, this is KW. Before I gave you K is 1 over KW. Okay, this is 1 times 10 to the negative 14. If you take the reciprocal, that's 1 times 10 to the 14. But I flipped it. Okay? It doesn't matter, as long as you're consistent. I've already flipped this thing, see? I don't have the 1 over here anymore. So this denominator is equal to this denominator. That's what I did here. If I want to solve for x.
Because every time I see KW, I'm trying to figure out if it's supposed to be equal to
10 to the negative 14. It is 10 to the negative 14. KW is 10 to the negative 14. But if you take...
Because you do the math and you flipped it.
Yeah. The KEQ for this reaction, this is the reverse of the autoionization. So the KEQ for this is 1 over KW. That's why I wrote this as 10 to the 14. Okay? So, what would this be? What's 2.5 out of 75? 2.5 divided by 75, multiply that by 10 to the negative 14. That gives you 3.73 times 10 to the negative 16. Is that right? Have 2.5 millimoles out of 75 mils. So 2.5 divided by 75, 0.03 concentration. Oh, I got it flipped. Sorry. I knew there was something wrong. Okay, this is times 75 over 2.5, right? If I solve for x. Sorry about that. This is times 75 over 2.5. Okay. Yeah. So now, what do? You say 75 times 10 to the negative 14 divided by 2.5. That's 3 times 10 to the negative 13. Okay, so 3.00 times 10 to the negative 13. That is your H plus, right? Okay, that's your X. That's a trace amount of H plus you have left. It's a very small number. Okay, what would be your pH at this point? Negative log of 3.00 times 10 to the negative 13. That would be, take the log of that and then take the negative. That's 1 point. It's going to be 12.5. 3 decimal places, so 12.522. That's your pH. So, does this make sense? Do we expect to have a very high pH at this point in the reaction? That's a high pH. High pH means acidic or basic? Basic. Do you expect it to be basic? 2.5 versus 5. You have no H, hardly any H plus left. You got a lot of hydroxide left unreacted. Okay? So you can use this type of calculation to solve the pH of your reaction mixture. If you were in the lab, okay, and you were to do in the lab, there's a procedure that you do in the lab called titration, where you have an acid here, and then you gradually add dropwise your sodium hydroxide to the acid, okay? And if you can monitor pH versus volume of titrant, this is called titration, so your sodium hydroxide is called your titrant, okay? Volume of titrant. If you were to monitor the pH of this mixture, what will happen? You start off with just acid, right? So you start with a low pH, and then the pH will gradually increase, okay? And you can calculate what these numbers, what the pH would be at every point in your titration if you want. If you make a plot like this, you get what's called a titration curve. What you'll find for a strong acid, strong base reaction is as soon as you get very close to the equivalence point where you have equal concentrations of H plus and hydroxides, when you get to the equivalence point, that pH is going to jump to 7. But a drop before that, like 0.05 mils before that, the pH is going to be low. It's something like 4. Okay? And then a drop after that, pH is going to be very high. So if you were to monitor this reaction, this is what you'll find. Okay? So if you use a pH meter in the lab for titration, it's a very good way to determine what's called the equivalence point. The equivalence point in this case would be at pH 7, okay, for a strong acid, strong base. So this is what you would call your equivalence point, where you have a 1-to-1 ratio of H plus and hydroxide mixed. Okay? Now, where are we on this titration curve as far as this problem is concerned? This example that we have a lot of hydroxide, right? And you've already consumed your H plus. So we're way past the equivalence point. So where would we be on this curve? Would be right around here, at pH of around 12 point something. Okay? So this big jump right here in the pH near the equivalence point is a very good way to determine the equivalence point of the amount of acid that you have in your flask by titration. Okay? Now what you can also do is you can add something that would change color when the pH changes by this much. And in the lab, the typical it's called an indicator. And typical indicator we use in the lab is called phenolphthalein. Okay? And phenolphthalein changes from colorless below pH 7, and it changes to pink above. Actually, it changes at around 9. Okay, but this one is a big jump in pH from around pH 7. So that's called a titration curve. Let's look at this one. This is a similar problem, except that this time we're dealing with a weak acid. So you have 25 mils of 0.1 molar sodium hydroxide and 25 mils of 0.1 molar HX. Okay, but this time you have a weak acid, and Ka of the weak acid is 1 times 10 to the negative 5. What's our reaction here? HX plus hydroxide will give you 1. H2O plus X minus. What's the equilibrium constant for this? When you're neutralizing, let's see if we can construct this from two reactions. You have HX gives you H plus X minus. What's the KEQ for this one? This is Ka of HX, right? And what's the other reaction we can use? We can use the autoionization of water. So you have H plus hydroxide gives you H2O. What's the KEQ for this one? 1 over KW. Right? So if you combine these two, what do you get? H plus cancels out, and you got the reaction you want. So what's the KEQ for this reaction then? K would be equal to Ka of Hx divided by Kw, right? Or here, times 1 over Kw. So what's the equilibrium constant for this reaction then? What's the Ka of Hx? 1.0 times 10 to the negative fifth. And what's 1 over Kw? 1 over 1.00 times 10 to the negative 14. This gives you 1.0 times 10 to the 9. Is that a large number or a small number? Large. What do you expect this reaction to do? Anytime you titrate a weak acid with hydroxide, typically you would have a reaction that pretty much goes all the way to completion. You have a large KEQ. Okay? So our we've solved our K here to be Ka over Kw, which is going to be equal to 10 to the 9. So let's solve this problem. Again, set it up as using initial concentration, changes, and equilibrium. Okay, so I is stable. What's our starting Hx? 25 mils times 0.1 is how many millimoles? 2.5 millimoles. What's the total volume that we have here? 25 and 25, 50 ml total, okay? So 25 millimole, okay, let me make that, 2.50 millimole out of 50.0 mils. What's my initial hydroxide concentration? Same thing, right? 25.0 millimole out of 50.0 mils. What would be my change? What's my initial x minus? 0, right? What would be my changes? Minus x, plus x, correct? But what's my x going to be? I know it's going to be a complete reaction, right? Pretty much. So I'm just not going to do it that way. I'm just going to say minus everything, right? And how much of this would I make? This is plus everything, which is 25.0 millimole out of 50 mils. Okay? So at equilibrium, what do I have left? Trace amounts of this, I'm going to call it x. And this would also be x, trace amounts. And here, what's 25 out of 50? That's 0.05, right? Moles per liter. So how do I solve for this, for the pH? I'm going to say that 0.050 over x squared is equal to KEQ, which is 1.0 times 10 to the 9. Actually, there should be a minus x here. Why? Because if you have trace amounts here left, then this is not fully 0.05. This is 0.05 minus x. Okay, so there's a minus x there, but we're going to ignore that because we know that that's going to be a small amount compared to 0.05. So to solve for x, what do you get? X squared equals 0.050 divided by 1.0 times 10 to the negative 9. 0.05 divided by 1 times 10 to the negative 9. 10 to the 9, sorry. 1 times 10 to the 9. Equals 5 times 10 to the negative 11. Okay, and so x will just be equal to square root of that, 7.1 times 10 to the negative 6. 7.07, let's keep an extra digit there. 7.07 times 10 to the negative, what was it? Negative 6. So that's your x. If you know x, what is that x? That's hydroxide, right? If you know hydroxide, what can you do? How do you determine pH from hydroxide? You can go POH and then go from POH, figure out pH, or you can just go straight to H plus, right? H plus would be what? 1.00 times 10 to the negative 14 over hydroxide, which is 7.07 times 10 to the negative 6. So 1 times 10 to the negative 14 divided by 7.07 times 10 to the negative 6 equals 1.41 times 10 to the negative 9. And your pH is going to be equal to inverse log of that. So take the log, the log of, negative log of that. So log times the negative of that, that's 8.85. So you can see your pH is basic at the equivalence point. Okay? Why are we saying this is at the equivalence point? You have equal moles of H plus and hydroxide. Okay? So if you did this titration, you did a titration curve for this, you're going to get something like this. This is pH versus volume of titrant. You're going to get a big jump, but your equivalence point is actually going to happen above pH 7. Okay? And you can explain that because you're saying, all right, pretty much what you have is you're out of HX. What you really just have is the conjugate of HX, which is a weak base. So X minus will give you a trace amount of, so a small amount of sodium hydroxide, and will give you it will hydrolyze. Okay, so you say your X minus. The way you explain that basic pH at the equivalence point is, at the equivalence point, you say the major species that you have is X minus, and that reacts a little bit with water to give you HX plus hydroxide. And so that explains your basic pH. Okay? So that's what happens at the equivalence point. Now, is there another way you can solve for the pH? You can go with the POH. Be a quick review. How do you get POH? Minus log of 7.07 times 10 to the negative 6. So you say 7.07 times 10 to the negative 6. Log of that, take the negative, that's 5.15. Oops. And so your pH would be 14.000 minus 5.15. So 14 minus 5.15 is how much? 8.85. So either way, you get the pH. Okay? So that's the equivalence point. So hopefully I've given you enough examples of these so that you can solve just about any problem dealing with equilibrium. It's not really possible for us to go into all the possible equilibrium problems. Okay? So keep in mind what you really need to do as far as problem solving strategy is write the reaction. Okay? And then get the KEQ. And if your KEQ is very large or very small, you're in luck. You can make simplifying assumptions. If your KEQ is not very large or very small, then you might have to go into actual solving of the polynomial solving for the roots of your polynomial, okay, quadratic equation. And this is more of the same, so I'm just gonna skip that. Let's try this one. Let's say you have a solution that is already 1 molar in HX and 1 molar in X minus. And you have 50 mils of that. And the pH, calculate the pH if Ka of HX is 1 times 10 to the negative 7. Okay, you're given Ka, so what equation are you interested in? HX gives you H plus X minus, right? And it says 1 molar in HX, 1 molar in X minus. So you're looking at initial conditions of 1 molar here and 1 molar here. Okay? So do you think this is going to go forward too much? Ka is 1 times 10 to the negative 7. Hardly, right? It's a very small Ka. So you can just say a small amount here plus X. That would be your changes. What would you have at equilibrium? 1.0 minus X over here, and this one will have 1.00 plus X. What simplifying assumptions can we make? Since this is small, we're going to neglect that, right? So we say Ka is equal to H plus times X minus over HX. So it's going to be X times 1.00 over 1.00. Okay. This is the beauty of problems where you have comparable amounts of a conjugate acid-base pair. Okay. Whenever you have comparable large amounts, okay, of a conjugate acid-base pair, they're not trace amounts, but you have finite amounts and they're comparable. Your problem is really simple because you can pretty much ignore changes in those. Okay, so 1 plus X would be the X would be negligible, the minus X here would be negligible. So Ka in this case will just be equal to X, right? So X would just be Ka, which is 1.0 times 10 to the negative 7. But what is that? That is your H plus, right? Right there. So that is your H plus. So what's our pH here? Negative log of 1.0 times 10 to the negative 7. It's going to be 7.00. Your pH is going to be 7. Okay. What happens if you were to add HCl to it? Okay. 0.05 mils of 1 molar HCl. What happens if it's contaminated? So a drop is about 0.05 mils of 1 molar HCl, 1 millimole per mil. That gives you 0.05 millimoles. What would happen? What would be the reaction this time? So you have your HX, right? H plus X minus. And you have your HCl. So you have your 1 molar here, 1 molar here. Okay, that's your initial concentrations. You can just ignore that H plus for now. You can say your HCl will provide, okay, since that's negligible, your HCl is going to give you 0.05 millimole over 50 mils, right? Actually over 50, 0.05 mils. Okay, we're just going to ignore the changes in the volume because that's just a drop. So we're just going to say out of 50, okay? That way we don't have to worry about changing the ones also. So this is going to be 0.05 millimoles out of 50. What's 0.05 out of 50? .001. Okay. What would be the changes? Which way do you think this reaction will go? You just increase the amount of H plus. You just added more product. Le Chatelier's principle says, which way will it shift? shifts to the left, right? So this is going to make plus 0.001, and this is going to be left with a trace amount, and this is going to be 1.00 minus 0.001. Okay, how do I know this is going to go all the way? What's the KEQ? What's the KA for this? 10 to the negative 7. It's very small, right? So I know that if this goes either way, it's going to go as far as possible to the left. So all of that 0.001 is going to go all the way. So at equilibrium, I'm going to have 1.001. This is going to be x, and this is going to be 0.9. What is it? 99? Right? So I'm going to say x times 0.999 over 1.001 is equal to Ka. Okay? So which is 1 times 10 to the negative 7. What's my x now? 1.001 times Ka over 0.999. 1 times 10 to the negative 7 times 1.001 divided by 0.999. That gives me 1.002 times 10 to the negative 7. Okay. You see much of a change? What's your pH this time? Still going to be very close to 7. This illustrates what's known as a buffer. Anytime you have a mixture that has comparable amounts of a weak acid and its conjugate base, comparable amounts, not trace amounts, okay? Comparable amounts, that solution tends to have a stable pH. It tends to be resistant to changes in pH by contamination. So this is what you would call a buffer solution. Okay, anytime you have a conjugate acid-base pair in solution that's in comparable amounts, then you have what's called a buffer solution. Okay, so a solution that has a stable pH is a buffer solution. It's not easily affected by contaminants. Okay, typically for you to have a good buffer, the ratio of the weak acid to the conjugate base should be anywhere from 1:10 to 10:1. The best ratio is 1:1, which we just illustrated in the previous line. Okay, now let's compare that to same amount of contaminant, 50 ml of pure water at pH 7 plus 0.005 moles of HCl, millimoles. No, 0.05 millimoles plus 0.05 millimole HCl. Okay, let's see what happens here. What happens to the pH? Well, what's your H plus going to be? Nothing's going to react with that H plus, right? Because all you have is a trace amount of hydroxide. 10 to the negative 7 is the most the water can give you. So that's going to be 0.05 over 50 millimoles per milliliter. So what's 0.05 over 50? That's still 0.001, same thing we had before. Okay, moles per liter. What's my new pH going to be? Minus log of 0.001. And that gives me log negative. That brings down your pH to 3 right away. One single drop of HCl that gives you about 0.001 moles will drop your pH from 7 to 3 right away. But if you put a weak acid, weak base in there, okay, in comparable amount, a conjugate acid-base pair in comparable amount, you have a solution with a stable pH. That's what you call a buffer. Okay? And I think we're running out of time, so we'll finish up the rest of this tomorrow.